Hey everybody, welcome back, and today what we're going to start talking about is direction in EAS reactions. Not directions like, you need to get a job, or go to college, or do something positive with your life, get off those antibiotics, break up with that guy/girl that you've been on and off with for the past 5 years. They're no good for you. I don't mean that kind of direction. The kind of direction I mean comes like this. Do you remember in every EAS reaction we have done so far, our starting material has always been benzene? Sometimes I've called it unsubstituted benzene. Sometimes I've called it naked benzene, because even benzene likes to have a little bit of fun. But what the point of that really is that the electrophile that you add, let's just nitrate for fun, 2SO4, you put the nitro group on there, and it's the first one on the ring. Okay? That means that there's none of those 6 carbons have any special preference one way or another toward where that nitro group goes. Direction actually involves, when you do EAS reactions on a substituted ring. Meaning, something else has already gotten to the benzene and planted their flag, so they kind of have squatter's rights and they can tell the next group where to go. Clearly, it's not that anthropomorphic. But in order to discuss this, let's talk about positions on an aromatic ring. And this is one of the last places in organic chemistry where old-style nomenclature really comes into play. And you're thinking, last times, fuck, every time I turn around, there's something new I have to learn. So this is going to be our substituent already on the aromatic ring, the R group. Now, every one of these carbons has an address, location, what have you, based on that R group. And we're going to learn the name of those now. Now, I'm going to give you the easy one first because you'll never have to say it again. The carbon that bears that R group is called ipso. That is the ipso carbon. Now, the only time you're ever going to have to learn about that is right now as I'm saying the words, and if you play some really strange bar trivia. So that is the ipso carbon. These carbons right here and here, that is 1 carbon away from the R group. These are called ortho. And there are 2 ortho positions or ortho sites on a monosubstituted aromatic ring. All right. As I switch colors to be clever, this here, this carbon and that carbon, these are called meta. Either the meta position, the meta site, etc. And finally, this one down here. Do I have yellow on here yet? I do not. This is called para. So that would either be called the para position or the parasite. No jokes, that's actually what it's called. Now, you know we chemists, we like to be very clever with our abbreviations. So, ortho, we can abbreviate as O. See how clever we are? Meta is an M. God, I bet you couldn't predict that. And finally, para is a P. Golly Martin, that's so freaking smart. Now, the other thing I want to do, and I'm going to have to write this one pretty small down here, is I want to consider that R group, all right, is either electron donating or electron withdrawing. How do you know that, Dr. Weigel? Well, I've established the R is anything other than a hydrogen. And since hydrogen is our baseline for electron donating and electron withdrawing, therefore, the R has to be one of the two. That's swell, Grandpa. Tell us another one. All right, so what I want you to remember is the every other atom pattern of partial charges on an aromatic ring. So you'll remember, hopefully, that for this R group, there would be a partial charge. Oh, stupid frickin' program. There'd be a partial charge there, a partial charge there, and a partial charge here. Meaning that ortho and para, locations, sites, whatever, ortho and para are usually linked. And meta, like the cheese, stands alone. So if we go back to our aromatic ring here, that means these three sites are either favored for addition there or disfavored for addition there, depending on the nature of that R group, which is going to be what we talk about for the next couple of lectures. The meta position here and here usually isn't any better for a direction, like if R happens to be a meta director, and we'll take a look at how you can know that over the next few videos. But if R happens to be a meta director, what it really means in a meta director is that meta sucks less than ortho and para. Sorry to depress you folks, but sometimes the best solution is only because it sucks less than something else. CF most of my dating career. Please don't tell my wife that. She's a fantastic woman and I love her dearly. All right, so what about an ortho para director? Well, an ortho para director works because the ortho and para positions are favored. The ortho and the para positions are somehow favored. So with ortho and para, those three sites are good. The EAS reaction is more likely to happen there for a couple of reasons we'll go into. With the meta director, the meta sites aren't really favored. They just aren't disfavored like the ortho and para positions are. All right, now there are two theories, two approaches to ortho, para, and meta directors. My intention is to give each one of these a video and then a third video at the end to kind of sum them all up. That way every one of these gets a chance to breathe. Now the two approaches for ortho and para direction and meta direction deal with partial charges and electrostatic attraction between the ring and the electrophile. And the other theory behind it, and both theories are right. It's not like they're in competition with each other. I just like to teach it both ways. The other theory deals with stability or instability of the cation formed during resonance. All right? let me reiterate. It's not like these are competing theories. They actually tell you the exact same thing. I just think I like to present both of them because then I think if one of them makes sense to you and the other one is just sort of then at least you have another option of understanding this. I'm going to bring this picture back into our lives because it's actually pretty important here. Because with the couple of additions that I made here, such as adding this ester over here, generally speaking, if it's an if it is an activator, it is ortho-para-directing. The exception being the 4 halogens here in the middle. All right? If it is activating or a halogen, it is an ortho-para-director. If it is a deactivator, it is a meta-director. All right? And I'm going to add to this, like I did last time, over here, where please remember that over here, all these attachments like there, here, all around, is where the aromatic ring is. Now, this is not a limiting list, and I should have brought this up in the last video, of these sorts of groups. For example, if you go back and rewatch my the conjugation and electron donation, electron withdrawal video again, you'll remember that this CX3, where X is one of the halogens, is very electron withdrawing. Therefore, is a deactivator and a meta-director. So that's it for this video. The next 2 videos we're going to do are the different approaches of understanding how EAS directors work. The first one will be partial charges and electrostatic attraction. The second one will be stability of the cation formed. And then I'll do a third, shorter video that kind of wraps it all up and summarizes it. All right, everybody, I hope you're doing well, and I'll talk to you again soon.